Hello, my name is Jeff Adams. This presentation will focus on brownfield characterization and remediation. First, let's begin with describing what a brownfield is. A brownfield is an abandoned, idled, or underutilized industrial or commercial site where expansion or redevelopment is complicated by actual or perceived environmental contamination. We see these all around us. Some examples may include former gas stations, automotive repair shops, abandoned industrial facilities, or vacant or underutilized retail centers, especially those that feature dry cleaners. In the United States, the EPA estimates that there are more than 450,000 brownfields. So why are brownfields important to our communities? Well, there are numerous benefits that come from the redevelopment. First, by cleaning up contamination that may exist, we can improve the environment and protect the communities in which the brownfield sites are located. We encourage land recycling, which preserves open and green spaces on adjacent and nearby properties. We can utilize existing infrastructure that had previously served a site, preventing the need to spend on unnecessary infrastructure to greenfield sites. Brownfield redevelopment increases the land value not only for the impacted site, but also for nearby sites as properties are rehabilitated. This can improve and increase property tax revenues for a community. Finally, we encourage job growth and community investment through brownfields, both with transient jobs associated with cleanup and construction, as well as long-term businesses that may find homes on the remediated sites. Looking at the big picture, real estate is considered the world's biggest asset class, with a worldwide value exceeding $233 trillion. Of this, $136.6 trillion worth of properties exist within the United States. So any way you look at it, real estate and brownfield redevelopment can enhance communities and provides a valuable asset in which communities may invest. When we have impacted or perceived to be impacted sites, we typically follow 3 steps. The first is the Phase 1 environmental site assessment. A Phase 1 environmental site assessment is performed for a property anytime there's a material property transaction, such as a purchase, a refinance, or an investment. They're performed on properties that are more complex than a single-family home. The purpose of a Phase 1 is to identify potential or existing environmental liabilities that may have come about from past site uses. The reporting follows US EPA and ASTM standards. ASTM 1527 is the designation. The double X's indicates that the standard is updated every so often. And the purpose of the report is to tell a story of the site history, of site uses that may have led to environmental impacts. Preparers typically consult such records as aerial photographs, topographic maps, title reports, environmental lien searches. They also contact numerous local, state, and federal public agencies to review files of any records of materials that may have been stored or used in such a manner where environmental impacts exist. Interviews are also performed with key site managers and owners of the property to determine if, in fact, there were uses in the past where environmental impacts may have come about. Many of the records I cited before can be ordered from companies who maintain proprietary databases and reports that outline past uses both on-site as well as off-site properties that could in fact impact the properties that are under consideration. A preparer will also conduct a site walkover, a reconnaissance of the property, identifying potential sources at the property or on adjacent properties, as well as current conditions that could result in environmental impacts. Ultimately, it's very important to identify any data gaps. In preparing these reports, were there any missing information or sources that could have been useful in material in providing an overview of site uses and a complete chain of history going back decades on the property? When preparing a report, the preparer looks to identify recognized environmental conditions that indicate known or material threats of environmental impact at the property. Ultimately, these RECs will drive whether or not additional work is warranted in the form of a Phase 2. I like to tell people that a Phase 1 is like going to the doctor for a checkup. You do the work, you do some tests, you look to see if there's anything of concern, and if you do find something in some of the testing, you may order up more tests to determine if there truly is an issue. Continuing with the medical analogy, the second step becomes the Phase 2 environmental site assessment. This is the step where actual testing of subsurface and surface media takes place. Of key importance to a Phase 2 is the sampling of soil and groundwater to collect soil and groundwater data. Traditionally, for many years, this was accomplished using rotary boring equipment. Such equipment can be used to collect both soil and groundwater, and in the case of groundwater, complex monitoring wells are installed. Both soil and groundwater can be collected and sent to a laboratory for analysis. Such an approach provides precise quantitative data. But such an approach is quite expensive, as the installation of monitoring wells and the use of rotary equipment is expensive and can be very time consuming. So in the past couple decades, there's been a migration towards direct push sampling equipment, which provides a cost-effective alternative to conventional rotary drilling equipment. It's faster, it's cheaper. The diameter of the probe equipment is much smaller than the diameters of the rotary equipment, which reduces investigation-derived waste. This equipment can be used both to sample soil and groundwater. Groundwater can be sampled directly through grab sampling, or either temporary or permanent packed wells can be installed within the boring to allow for continuous or intermittent sampling. Soil and groundwater studies remain key to Phase 2 site assessment, but in the past couple decades, vapor intrusion studies have become increasingly important. With vapor intrusion, volatile chemicals migrate from contaminated soil or groundwater into structures where they may pose a health risk to occupants. In order to perform a vapor intrusion study, it's important to collect specific soil vapor data and then take into consideration several site-specific parameters, including the type of soil, the properties of the contaminants that may be present, the building and the foundation design, and the duration of potential exposure based on the type of use of the structure. All this data is input into a conceptual site model. Soil gas samples may be collected directly from the subsurface using either temporary or permanent sampling wells. It's important when sampling to determine if the sampling apparatus has leaks that are present. One method is to use a shroud where an inert gas is placed within the environment of the sampling apparatus. Another such method is to place rags that are doused in chemicals that aren't typically found in the environment around connections or fittings. In either case, if the leak detection compound is detected, it calls in integrity issues with the sample, which may void the sample's use. Sampling is typically performed following either state or federal guidance. If our soil or groundwater or soil gas sampling has identified some type of environmental issue that may pose a threat to environmental or public health, typically above a range of screening levels that have been established for any number of chemicals, we may want to consider some type of remediation for the situation. If we do have a situation that requires mitigation or remediation, the first thing we do is develop a conceptual site model, which will allow us to come up with a remedial implementation strategy. A conceptual site model factors in the contamination that may be present, the site use, the potential site use, as well as several physical characteristics associated with the site, including depth of groundwater, direction of groundwater flow, and soil type, or bedrock type. We factor all of these into consideration and try to determine how people may be exposed to contamination during site use, either currently or for a proposed use. The most common way to address impacted soil is through excavation. Simply put, we use heavy equipment like bulldozers or loaders or excavators to remove soil from the subsurface, such that remaining soil at the base of the sidewalls does not pose a threat to the environment or to public health. It's a fast and effective method. It's cheap. There are many providers, contractors that is, that can perform the service. But from a disadvantage standpoint, it's holistically expensive. It does create material that needs to be off-hauled and taken to some type of appropriate disposal facility, which creates traffic and emissions related to trucks, as well as wear and tear on roadways. Also, if there are improvements present at the site, such as parking lots, structures, utilities, or other infrastructure, this can pose a risk or prevent digging from taking place. It also has fallen out of favor recently with regulators just because of all of these issues. You are creating something that still needs to be disposed of, you create emissions, and from a sustainability standpoint, it's just not quite favorable. Pump and treat systems have been traditionally used to address contaminated groundwater. Well networks are installed that are used to extract contaminated groundwater or free-phase product that may exist on or within the groundwater table. It tends to be efficient and effective at removing free-phase product, but once the free-phase product has been removed, it's not nearly as efficient at removing dissolved phase impact. As a result, there's an asymptotic relationship where removal rates drop drastically with increased time. As a result, pump and treat tends to be fairly inefficient to meet cleanup goals, can be expensive, and can be time consuming. Given the limitations of soil excavation to address soil contamination and pump and treat systems to address contaminated groundwater, a number of approaches have been developed in the past 25 to 30 years that are used to treat a variety of contaminants and a variety of contaminated media within the subsurface. Soil vapor extraction is a common approach to treat vadose or unsaturated zone impacts. A well network is installed and tied into a vacuum, which induces soil gas flow into and out of the well network. During operation, contaminant mass is removed through a variety of mass transfer and transport processes, including volatilization, advection, diffusion, and desorption. As mentioned, this approach is only applicable to vadose zone impacts. Additionally, it's best used in high permeable soils. It's not very effective in low permeable or stratified soils. Air sparging is a similar technology to SVE, although it operates on an opposite manner. Air is injected into the subsurface below the lowest known level of contamination. The air, through the effect of buoyancy, will rise towards the subsurface and remove mass through a variety of mass transfer and transport processes. An air sparging system is commonly paired with an SVE system for removal as well as to control the injected air. Air sparging may be used to treat impacted groundwater, but like SVE, it is best to use in homogeneous or permeable soils. With in situ chemical oxidation and reduction, reagents are injected into the subsurface where they interact and will break down the contaminant mass. Depending on the reagent used, as well as the contamination that may be present, the contaminants will be either chemically oxidized, meaning they lose electrons, or reduced, gaining electrons, during the chemical reaction. The goal is to convert the contaminants into harmless byproducts, typically carbon dioxide, water, or salts. The approach works well in both saturated and unsaturated soil and can address a wide variety of contaminants in a wide variety of soils. However, it's very important to know what chemical reactions will take place because in some instances, harmful byproducts can be generated. Additionally, you are injecting reagents into the subsurface, so injection permitting with public agencies is a necessary task. Whereas in situ chemical oxidation and reduction relies upon chemical processes, enhanced bioremediation or bioaugmentation relies upon biological processes. The goal is to utilize microbial populations that exist within the subsurface to break down the contamination that may have been introduced. Typically, contaminants are broken down through oxidation. Oxygen is the electron acceptor, and this occurs through aerobic respiration. This is similar to any type of living being breaking down food products through aerobic respiration. In some instances, there may be a limiting factor in the potential for bioremediation, and enhancements need to be added, either through oxygen, nutrients, or co-metabolites. In some instances, microbes can actually be introduced into the subsurface. In this instance, it's referred to as bioaugmentation. It's an effective method regardless of the type of soil and can address a wide variety of contaminants, but it's important to monitor it closely because the reactions will only take place when conditions are ideal, and it's important to maintain those ideal conditions. Nature is amazing because it can heal itself, and if conditions are ideal within the subsurface, contaminant mass can be broken down. This is more than a leave-it-alone approach, hence the name monitored natural attenuation. The goal is to let natural transport, transfer, and transformation processes take place to reduce or eliminate contaminant mass. It's important to monitor conditions through monitoring well networks as well as other instrumentation, because number one, during reactions, daughter products that are generated may be more toxic than the original parent products that existed within the subsurface. Secondly, in some instances, the pollution or impacts will migrate, and it's important to make sure that downstream sensitive receptors are not impacted by any type of contaminated mass that may be migrating. It's also important to ensure and confirm that the breakdown will take place in a reasonable amount of time. The previous examples focus on approaches that break down or remove contaminant mass. In some instances, it may be more appropriate or more cost-effective, or both, to allow the contaminant mass to remain within the subsurface, provided protective conditions are introduced. In some cases, it may be appropriate to allow contaminated soil, contaminated groundwater, or both to remain at a site, provided that a protective containment structure is installed. Such a structure consists of several elements. First, a cap may be installed. This often consists of either clean soil, geosynthetics, or paving material, or a combination thereof. The idea is that it prevents rainwater from infiltrating into the contaminated mass, but more importantly prevents humans or wildlife from burrowing into and encountering impacted materials. Often a low permeable inclusion, either soil or bedrock, may provide bottom containment of the impacted mass, but in some instances it may be appropriate to use horizontal drilling techniques to provide such protection. Lateral structures may also be installed. Vertical slurry walls or vertical sheet pile walls may be installed. This prevents the mass from migrating outward. It's common to place instrumentation, like monitoring wells, into the mass as well as around the mass to make sure the contamination stays within the containment structure and doesn't migrate outwards, impacting nearby soil or groundwater. It's also common to provide periodic inspections to make sure the containment structure is functioning as intended. Sometimes it's infeasible to address contamination that may exist at a site, either due to on-site impacts or migration from off-site sources. Contamination in the form of volatile chemicals can pose a vapor intrusion risk to structures. It's increasingly common to install vapor intrusion mitigation systems, either within existing structures or as part of a new construction project. These systems typically consist of a combination of a vapor barrier, an active or a passive venting system, or both. It's also common to include provisions and equipment for long-term sampling and collection. The attached figure shows a typical detail for a vapor barrier system combined with a passive venting system. When contamination is allowed to exist at a site, either within a containment structure or through the use of a vapor intrusion mitigation system, it's quite common to provide some type of legal control for the property. This is typically done through a deed restriction or a land use covenant. Such legal instruments typically prohibit various on-site activities, such as installing wells or digging through into the subsurface without permission of an oversight regulatory agency. There may also be provisions for periodic inspections as well as long-term monitoring to ensure public safety. In the past few years, approaches to environmental contaminant remediation focused on getting the job done. But there is a realization among practitioners and regulators that it's important to take a look at a bigger picture, to take a look for holistic approaches that solve the problem, but also are respectful of and ensure sustainability for the greater system of the environment. Green and Sustainable Remediation, or GSR, is an emerging approach that provides a holistic approach to environmental remediation with the goal of minimizing ancillary environmental impacts. The goal is, of course, to have efficient remediation approaches that protect air, water, and soil, but also to consider such things as potential for emission, potential stressing of infrastructure, and added waste burden that may result from impacted activities. Think of it as environmental remediation that stresses the triple bottom line, where there's a move to optimize the outcomes from an economic, social, and environmental standpoint. Of course, remedial efficacy and efficiency are paramount, but also with GSR, we look at ways to reduce energy consumption, perhaps incorporate renewable energy resources, minimize or reduce GHG emissions, or find a way to sequester GHG emissions, and find ways where remedial technologies may be applied that do not require off-site waste disposal of impacted materials. Continuing with the framework, there is a greater emphasis on using recycled or reclaimed water as opposed to fresh water, and recycled materials as opposed to first-use materials. It is always desirable to have a remedial approach that will drive something to an unrestricted land use designation to allow for a highest and best use for whatever that property potential may be. But it's important to provide a cost-benefit analysis because in some instances, it may be more appropriate to remediate a property to a commercial or industrial land use than an unrestricted residential land use, because to do so may be exponentially more expensive. Put another way, it may be better and more efficient to remediate it to a lower use and place engineering controls in place because it may overall be more cost-effective. All of these concepts within this framework are assessed against a range of factors and metrics to determine the best way and the most efficient or holistic way to remediate properties. The following is a list of common metrics that may be applied to do this cost-benefit analysis. In the past several years, the EPA has grouped some of these metrics into 5 categories: energy, emissions, water, materials and waste, and land and ecosystems. Common GSR energy-related metrics focus on total energy used, as well as the percentage of energy that may be used from renewable resources. Emissions factors take into consideration of greenhouse gases, other criteria pollutants, as well as other hazardous or non-hazardous pollutants. Water-related metrics factor on the total use of water, the sources of waters, as well as the potential how a system may draw down groundwater. Materials-related metrics focus on the types of materials used at a site and in a remedial project. Are we using first-use materials, or are we somehow repurposing or recycling materials? What are the quantities and what are the percentages of these materials? Are we working with bulk materials to save money and save packaging? From a waste standpoint, are we finding unique ways to retain waste materials on site in some type of productive manner? Are we generating hazardous waste during a remedial project? Are we taking potentially hazardous waste and finding a way to render it as non-hazardous before it's either disposed or retained on site? And from a land and ecosystem standpoint, are we finding creative ways to recycle or repurpose land? Are we preserving green spaces, or are we finding ways to take formerly brown or gray spaces and turning them into green spaces? So I'd like to conclude with some challenges and need that not only focus on GSR, but also the greater environmental remediation universe. First, it's important, regardless of the size, scope, or approach of a remediation activity, to provide education and training for all stakeholders that may be involved. Any type of remediation is going to impact the built environment, and as such, there's going to be a wide and diverse range of stakeholders. Communication is necessary. Everyone benefits when there is a use of guidance documents that have clear and consistent definitions, as well as standardized metrics and validated evaluation tools, so everybody is playing from the same scorecard. When specifically dealing with sustainability, it's best to stick with well-defined frameworks that are well understood, have been validated, and are respected across numerous stakeholder groups. Regardless of a remedial approach, anytime one can demonstrate proof of concept, it's going to be beneficial. So pilot studies and case studies are always helpful, especially when they involve sustainable remedies that may be just evolving. Specific to GSR, and acknowledging that we have a relatively antagonistic political environment, we still will need to rely upon and provide incentives to adopt sustainable remedial strategies. And additionally, we need to support research and development of evolving and innovative GSR approaches. Finally, we rely upon those government officials, be it at the local, state, or federal level, to push and promulgate regulations that require GSR for environmental cleanups. And with that final point, I conclude my presentation, and I thank you for your attention.